Thank you for this introduction, Denis. It's a pleasure to be here and to speak about this work. And this work is related on how to do model choice when you have an intractable likelihood and when you are faced on big problem with respect to the calculation of the likelihood. So this is a joint work. I will present a couple of papers with joint work with some of my colleagues, Natesh from Harvard, Christian Robert from Dauphine, Judith Rousseau from also Dauphine. And this is a PhD of mine, Coralie, Pierre, which is an assistant professor in Montpellier and work also on this type of question, and Mohamed, who has done a PhD on ABC methods also with us, me and Christian. And so I will try to introduce the ABC techniques and how we can use these techniques in order to do some model choice. And there is a lot of open questions and a lot of difficulties, and I will try to show you how we can solve some of them and how some of them remain difficult to manage. Okay, so let me first introduce some motivation, and we suppose that the likelihood function is expensive or impossible to calculate, and in this case it's extremely difficult to sample from the posterior distribution, and there is two typical situations in which the likelihood is almost intractable. The first one is that you have a big set of latent variables and you are not able to integrate over this large set of latent variables, and so the likelihood of the observed at the parameter value theta is unavailable because you are not able to compute this integral over the latent variable set. And the second typical situation is when the normalizing constant of the likelihood is not available too. So this is, for example, the case for some Gibbs random field or Markov random field. So this is another type of model for which you have a difficulty to compute the likelihood. So I will be in this setup. I suppose I cannot compute the likelihood, and I also suppose that I am not able to define a Monte Carlo approximation, let's say an important sampling approximation in this case of the likelihood function. And I would try to avoid this approximation of the likelihood by using some simulation with respect to the model. And that's the ABC idea. So ABC for approximate Bayesian computation is a technique that only requires being able to sample from the likelihood. And this technique comes from the population genetics community about 15 years ago. And population geneticists still significantly contribute to the methodological development of these techniques. And let me first, to motivate more the problem, introduce some concept of population genetics. And I have to confess that if with Christian we work on ABC method, we have to be very grateful to our biologics colleague, because the first time they came to us to introduce this type of techniques, we are very skeptical and we say, okay, guys, how can we expect it works? You introduce another approximation. Don't you think we have enough of approximation with MCMC or ABC stuff? Now you want to approximate also the likelihood function. It seems to be too difficult to do that, and they spend a lot of time to convince us that it can work, and I try to convince you that also in some cases it can work. So this is Jean-Marie Cornuet from Montpellier, which is a specialist of the Western ONEB, and this is Arnaud Estub, which is a specialist of the Asian ladybird beetle here. And typical Arnaud and Jean-Marie question are, okay, how the Asian ladybird beetle arrive in Europe? Why do they swarm right now? What are the routes of invasion? How to get rid of them? This is the typical biological question they have. And in order to solve this type of problem, they are using molecular data sampled at the present time and try to infer on the link between different populations. That's their goal, okay? So they use a lot the King-Bank coalescence process and ABC inference procedure, and the first ABC was designed based, or let's say, on some sort of coalescence process. And the King-bound coalescence process is concerned with the genealogy of a sample of gene back in time to the common ancestor of the sample. And this is a within population model. So for each population, we consider a coalescence process. So this is this type of coalescence here thing. So you have to estimate some parameters which are, for instance, the mutation rate and the effective population size for one population. But this is not exactly the problem of our biologist guy. Our problem is to link the different populations. So for each population, we have a coalescence process. So imagine here you have a sample of POP1, a sample of POP2. For each population, we have a coalescence process. And between populations, they consider three types of different events backward in time. What they call a divergence. A divergence is a fusion between two populations, let's say backward in time. They consider some admixture, which is a split of population in two parts here, backward in time too, and also some migration process. And their typical problem is to try to discriminate between different population scenarios from a data set of polymorphism, let's say a DNA data set, observed at the present time. So here is a scenario we infer for the honeybee in the thesis of Mohamed. So we have observed at the present time 4 populations, and this is one scenario to link these 4 populations backward in time. Okay, so typically this population 2 come from come from an admixture between a non-observed population who have a divergence time T2 from population 1 and an observed population 3. And this is one scenario here, and we have some other type of some other possible link between population, and we would like to discriminate between these different scenarios. For instance, we can consider that there is no migration process here, and this is another model. Okay, so typically, let's see an example which is also a data set we use. Is concerned with the worldwide route of invasion of Harmonica axiridis. And for each outbreak, the arrow indicates the most likely invasion pathway and the associated posterior probability value here, estimate using an ABC procedure. And you see, this is the route of invasion of these species here. And so they would like to infer this type of question. Where come from this population here? And is it coming from the native area, or is it coming from another area? And then they have to decide between some different scenarios, and in order to do that, they observe at the present time some DNA data set. Okay? So here, this is also a graphical representation of the scenario with admixture we finally infer and select for this type of data sets here. And we have also some inference on the parameter once you have chosen a model. Okay, so this is a real model choice problem. And for one population, if you consider for this type of king-bound coalescent process, if you consider only one population, the joint likelihood of the genealogy and of the polymorphism observed at the present time is available. Okay, you got it. But the genealogical tree is a Nison's parameter, and the calculation of the likelihood for the parameter involves integrating out the unknown tree. Okay, and this is the reason why we are in an intractable likelihood problem. And we have this for each population, and we have more than a model for one population. We have also a genealogy between the population. And when we infer the genealogy and the link between the population, it's a model choice problem. And the intractability comes from the likelihood that correspond to each coalescence process which is not available, okay? Because the space of genealogy is so huge that you are not able to integrate out with respect to the constraints that the observed DNA at the present time is consistent with the genealogy we would like to integrate it out. So it's almost impossible. And this modeling differs from the phylogenetic perspective, where the tree is a parameter of interest in the phylogenetic perspective. So in the population genetics, we are not interested in the tree. We are interested in link between population and estimate the parameter associated to the population scenario, times of divergence, time of admixture, and also parameter for each population, mutation rate, migration rate, something like that, okay? And choosing a population scenario is a model choice problem, okay? So our Jean-Marie and Arnaud come to us with a typical model choice problem and try to solve this problem by using ABC approximation, okay? That's the motivation. And so here we consider a collection of capital M models, and we are in the Bayesian paradigm, so we put a prior on the parameter of each model, and we also put a prior distribution for the model index. And as all here know, the Bayesian model choice is driven by the posterior probability of the model given the observed data. And here you have, let's say, a double or triple intractability problem, because you are not able to compute this integrated likelihood with respect to the prior distribution, and even the likelihood function is not available, okay? So we have a double, let's say, intractability problem, and a triple if you consider another more type of complex model. Okay. So let me now let this biologist population genetics motivation and come from the standard ABC things, and let's first consider parameter estimation. So it's extremely intuitive and extremely easy to understand. So what you do, you sample a parameter from the prior distribution, you generate an associated data set, you compare based on the summary statistic and on well-chosen distance the simulated data set to the observed one, and you keep the parameter value for which the distance between the corresponding simulated data set and the observed data set is small enough. Okay? So you try to simulate data sets which are close to what you have observed, and you keep with you the value of parameter which give you a simulated data set close to the one you observed. This is extremely intuitive and extremely easy. And you don't need to calculate the likelihood, but you have to be able to simulate from the likelihood, okay, here, in order to get some simulated data set. So just one point, if you are in a countable set, and if this distance is exactly equal to 0, the parameter value for which the simulated data set is exactly equal to the observed one come exactly from the posterior distribution. That was the previously like a free rejection sampling algorithm. And then there is some extension to not countable space and to introduce this threshold. So for such this is a Monte Carlo, and this is a rejection algorithm for this target. And this target is the product of the prior multiplied by the product of the likelihood multiplied by this indicator function, which is equal to 0 if the distance is greater than epsilon and is equal to 1 if not. And the idea between these techniques is that the summary statistics coupled with a small tolerance should provide a good approximation of the posterior distribution. Okay, here. I will come back to that point. So let's first see a toy example introduced by Richard Wilkinson in a tutorial on NBC in NIPS last year. So consider you have a Gaussian distribution with parameter theta, and the parameter is in the expectation and also in the variances. Consider a uniform minus 10, 10 on theta. Consider that you have observed a while equal to 2, and that you take a L1 distance here between your simulated and your observed data set. So what happened? It's just a very quick illustration. In black, the black curve corresponds to the true posterior distribution of theta given while equal to 2. And the red dotted here corresponds to the ABC approximation. And what you see, okay, here this is the simulated value of theta. Here, this is the value of while. Okay, and then if you take an L1 distance, you have these two bonds for the while you accept, and you keep with you the corresponding theta, and this is just a kernel approximation in dimension 1 of the posterior corresponding to the theta you keep with you here. And what you see, if you decrease the value of the threshold, the approximation become better and better, and okay, if epsilon is equal to 2.5, you get this, and if epsilon is equal to 1, you finally get a quite good approximation to the posterior distribution. That's the idea. If you decrease the value of epsilon, you will get a better and better approximation to the posterior distribution. If epsilon tends to 0 under some quite standard, let's say, regularity condition, you have a convergence of this ABC target to the true posterior distribution. Okay, that's the point. This is okay. I have to say also that there is an MCMC sampler target for the ABC approximation, and this ABC sampler consists of generating a theta according to a Markov kernel Q, generating a new value of an observed data set, and as you can see here, the acceptance probability does not depend on the likelihood. So you have this ABC sampler for this approximation to my posterior distribution, and the likelihood ratio of the acceptance probability, does not involve any likelihood calculation here. You can see that your acceptance probability is equal to this, and this can be decomposed to this guy to this is a product here, and then the value of the likelihood cancel. Okay, and then there is an MCMC sampler which is designed for the ABC target, and which does not involve any calculation of the likelihood here. And but you need also for the rejection sampler to be able to sample from the model. You need to be able to sample exactly from the model. Okay, one remark. Look, this is the ABC target, and it can be viewed as a convolution approximation to the posterior distribution, and I think this is exactly what happened. Look, if you divide here by the normalizing constant of the posterior, here and here, so you get the posterior distribution. You get the posterior distribution here of theta given z here. So this posterior to here, and the ABC approximation for the posterior distribution of theta is a marginal over z of this guy. And so if you integrate over z, you have this kernel, which is a standard rectangular kernel here. And so this corresponds to a convolution approximation. You can write this exactly like this. And then you can change the type of kernel which is used here. Okay? You can use more smooth kernels than compared to the standard rectangular ones here. Okay, and one point extremely important is there is three types of approximation using this algorithm. First, we have summarized our data set, and I will explain here why we have to summarize. We have to summarize your data set here. So it's extremely difficult to have a summary statistics which is a sufficient statistics. Okay, so you have a first approximation, a loss of sufficiency by summarization. The second approximation is you change of target. So you start from the posterior and you decide to forget the posterior and to consider this target instead of the posterior, which depend on the value of the threshold epsilon. Second approximation. And the third one is a more classic one. It's a Monte Carlo approximation, because you use a reject or MCMC sample to get some sample from this target. So there is three type of approximation, and one is we have to summarize. And if not, the distance value are too noisy. And what happened in the exponential family case? We use sufficient statistics. Outside it's difficult. And typical for our population genetics model, we do not have any sufficient statistics. So we have a lot of information, and I will concentrate it a lot in the next part of the talk. And let's see a toy example. The reason why we have to summarize, but it's quite intuitive. But the simulated, let's consider that the simulated summary statistics and the observed one are ID with uniform distribution on 0, 1 power d. Here, the dimension d, space of dimension d. And look here. So we consider the value of the distance for a value of d which is equal to 1. So when the value of n increase, okay, the value, so you take the minimum in the infinite norm between the observed and the simulated, so that should be a z and a y here. Okay, and you take the expectation of this here, and it's quite easy to decrease this value for small value of d, and when the value of d is large, let's say 200, it's as you can say, it's extremely difficult to decrease the value of this expectation. So the distance is very noisy, and the minimum of the distance in the infinite norm will not decrease a lot by using 100 simulation on 100,000 simulation. Look, okay. And you have a lot of noise, and you have a curse of dimensionality. So this is the reason why you have to summarize. We cannot compare directly the observed data set to the simulated one. Here. So more other type of work had been done to design adaptive sampler. Why? Because look here, there is a loss of efficiency by simulating from the prior. If the prior is far away from the posterior distribution, you put some value of theta everywhere in the space, and you take a lot of time to simulate value of z for not interesting value of theta we are put everywhere. So we can try to design some adaptive sampler and to modify the way you simulate the value of theta. And there is a lot of work in that direction. And there is various sequential Monte Carlo algorithm, and the first one is the one of Sisson in PNAS in 2007. And corrected, there is a bias things in this partial rejection sampling idea here, and we corrected and proposed an alternative in the Biometrica paper. Then there is a paper from Arnaud here with Adje and Pierre in statistics and computing, which is a sequential Monte Carlo ABC. So the idea is always the same. You decompose the difficult problem of sampling from this target into a series of simpler sub-problems, and at time 0 we start with a large value of the threshold, and then you try to decrease the value of the threshold during the iteration. And the idea is to use the approximation of the posterior you get at time 0 to sample from this at time 1 and avoid a sampling from the prior, because we are supposed to have a more and more close to the posterior approximation, and then to put the value of theta in the right part of the space here. So there is some different way to calibrate it, the decreasing value of the threshold and the kernel we use to simulate, and there is this serious paper. And there is is just a subsample of the paper in this area, and there is some other here. Moreover, there is an alternative introduced by Mark Beaumont in 2002 and other, David Boulding and Zhang, to rejection at IBC. And the idea is to use a post-processing adjustment of the parameter value to try to weaken the effect of the discrepancy between Z and Y. Z is the simulated and Y is the observed. Okay, and there is two key ideas in this regression adjustment. The first one is to use a non-parametric kernel density estimation to emphasize is the best simulation here, because look, after with a rectangular kernel, so we accept or reject value of theta and then we forget the weight, but there is some weight still in the distance is a weight here. And the second point is to learn a model from the conditional expectation. Why? This is the reason why, because this non-parametric kernel density has also a curse of dimensionality here. And so to avoid this curse of dimensionality, so we reintroduce the weight by a non-parametric argument, but we define a parametric model for the expectation of theta given y, let's say the approximation of the posterior distribution, to get some sort of parametric rate of convergence compared to these non-parametric things. This is the idea of Beaumont, and there is some development in Bloom and Francois in statistics and computing. This is a local linear regression adjustment in Beaumont, and this is an heteroscedastic nonlinear and neural network adjustment in Bloom and Francois. And there is also a lot of works in the link between non-parametric statistics and ABC. Look, it's normal because what we do, we simulate a large number of theta, a large number of observed of new data set, and we would like to estimate a conditional density, okay? And we would like to estimate a conditional density, and we are able to fix the number of points we have to estimate this conditional density because you simulate this point. But so there is some link between non-parametric statistics and ABC approximation, and also a paper of Bloom in JASA in 2010, and also some other paper to see the connection between the two things. So, and this is more or less related to this regression adjustment of Beaumont here. One central question I would like to emphasize today is how to choose the set of summary statistics. So there is how to choose the distance, how to choose the threshold, how to choose the set of summary statistics also. And how to choose the set of summary statistics is for us one of the central questions of this procedure. And for parameter estimation, there is some proposal. For instance, Joyce and Marjoram, Nunes and Boulding, Paul also and Dennis propose a nice paper for a sort of semi-automatic ABC choose of summary statistics for parameter estimation. This semi-automatic is based on the first ABC approximation, and then use this first ABC approximation to construct a set of interesting summary statistics in an iterative thing. There is also this nice paper of Bloom and co-authors in statistical science. We review all procedure to choose a set of summary statistics and to summarize, so to reduce the dimension in statistical science. And there is also some work on the model choice, and I will come now on the model choice question, and a paper also from Bart and Sarah and also Michael Stumpf in statistics and computing in 2012, and also a paper, I think it's perhaps Pranger. You are the first author of this paper. Yes, sorry. So it's Pranger and Paul is involved or not?
Yes.
Yes. Oh. So I just make a permutation of the author name, sorry. So this is also a proposal which is linked with this one, which consists of to have a first ABC approximation and use the first ABC approximation to design a set of summary statistics with the idea that the base factor is the best summary of the base factor. This is more or less something like that. Here. And we also publish a paper which is related to this scheme here, where the paper we published here in molecular ecology, and in this paper we propose to use a linear discriminant analysis on the summary statistics in order to reduce the dimension. So they have a large set of summary statistics in population genetics for the different scenario here, and we use a linear discriminant analysis with Christian Pierre and other to reduce the set. Okay, and also now I arrive to the main part of my talk, which is related to what about ABC and model choice? Is it possible to have a good or a confident enough model choice procedure when you do this type of approximation here? And one very important point is the way you will summarize your data set. Okay. So before that, we published also 2 papers in bioinformatics and 2 software to infer about this population history. The first paper in 2008, which is the software is called DIY ABC, Do It Yourself ABC, which is a bit okay, which is a software dedicated to biologists, but not so easy to use and not completely yourself. Okay, and there is a version 2 which consider more markers, and in the first version we only have microsatellite marker, and now we have a software for SNP marker and also directly DNA sequences observed at the present time. Okay, okay, but look, in 2008 we proposed this software where there is a rejection ABC model choice and also some other some sort of local logistic regression to have an equivalent to the non-parametric post-processing of Beaumont within the model choicings. Okay, so this is not only rejection, but we propose this, and we consider that the set of summary statistics provided by the biologist guy is contained enough of information. Okay, and then after we decide to have a look more intensively on this problem. What happens if we have not enough information? And so let me first introduce the ABC model choice reject algorithm, which is extremely simple. I just add one line, so I sample a model from the prior, then I sample a parameter for the corresponding model, and I generate a data set for the corresponding model parameter, the couple here, and I compare based on also a well-chosen distance and a well-chosen summary, and I keep with me the value of the model index for which the distance is small enough. Okay, so this is exactly the same process as before, because this is normal because I am in the Bayesian paradigm, and I put a prior on the model index, so the model index is just now it is a part of theta. It's just a discrete parameter I have to infer, and I have decomposed in 2 parts this, but I have a big parameter space which is composed of the index parameter index as all the parameters of each model. Okay, so first, if eta of while is a sufficient statistic for the model choice problem, this can work, let's say, pretty well. You need to have a lot of computational power. I will, in the conclusion, in the discussion, I will say one word about that. But if you have enough computational power, okay, it can work. And we published this paper in Bayesian analysis to see how it works to discriminate between some Gibbs random fields here. And the question now is, what happens if your summary statistic is not sufficient? Okay, and what we observed first 5 or 4 years ago is that there is essentially no work on sufficiency and model choice. Okay, so a sufficient statistic for a model choice problem is a statistic such that the conditional distribution of while given eta while does not depend on the model index. Okay, so you have all the information with respect to the model index. And what we observe is that asymptotically speaking, a loss of sufficiency can be a real difficulty for model choice question, and I will try to show you why. Okay, so let's consider two models, model 1 and model 2. So you have these two likelihoods, and let's consider that eta 1 is a sufficient statistic for model 1, eta 2 is a sufficient statistic for the parameter of model 2. And if you take the knot is rarely, not forget the knot here. If you take the concatenation of eta 1 and eta 2, it's rarely sufficient for also the model index. Okay, so concatenation of sufficient statistic for parameter of each model does not give you and rarely give you sufficient statistics also for the model index. Okay, and there is a fundamental discrepancy between the standard Bayes factor, let's say Bayes factor or posterior probability, and the Bayes factor based on summary statistics. And I can show you this discrepancy. So the Bayes factor is a ratio of integrated likelihood. So the standard Bayes factor is this, and this is a Bayes factor based on the summary statistic eta while here. So here, instead of having the likelihood, you have the likelihood corresponding to eta while here. And if eta is sufficient for both model, for the parameter of both model, you have taken the concatenation of eta 1, eta 2 for both parameter of model, eta is a sufficient statistic. You have this factorization theorem. You can write f of while given theta I, which is a function which only depends on while multiplied by a function which depends on theta and on eta, and on while only by using eta while here. And so if you plug this here in this formula, you get this connection between the standard Bayes factor, so the Bayes factor based on the whole data set, and the Bayes factor based on the summarization corresponding to eta. And what you see is that there is a link between these two quantities and up to a constant which depends on the observed data set. And that's the problem. And this can take, if the summary statistic is not well chosen, it can take, let's say, any value, and it can give you some sort of not consistent model selection. So this equality was observed in the paper of us in PNAS, and also a paper of Didelot and co-authors in Bayesian analysis at the same time. And what I say, unless we have G1 equal to G2, this is the case for all sufficient statistics. So this is also the case for the Gibbs random field. And the two Bayes factors differ from this ratio. And what we emphasize in this paper is that the magnitude of difference can be such that there is no direct connection between both answers. Let's see an example. So let's consider that model 1 is a Gaussian with unknown expectation theta 1. Model 2 is a Laplace or double exponential distribution with unknown mean theta 2 and scale parameter 1 over square root of 2, which give you a variance is equal to 1 to the corresponding distribution. And let's suppose that you observe an ID sample from N1 and M2 here, exactly. And we consider these four, let's say, statistics. Naturally, it's perhaps too strong. These four statistics can be considered. First, we can consider the sample mean, which is sufficient only for the Gaussian model. We can consider the sample median. This is not sufficient, but its distribution depends on theta I on both models here. We can consider the sample variances, which is an ancillary statistics because the parameter in each model is correspond to the expectation here. And we can consider at the end the median absolute deviation, which is called the MAD, which is an ancillary statistics with different asymptotic expectation under model 1 and model 2. And this is an important point, and I will come here later. And look, here on the left, the true model you simulate from model M1, so the true is a Gaussian. Here on the right, the true is a Laplace. And what you estimate the posterior probability of the Gaussian model. Okay? So if it works, this should concentrate this to 1 and this to 0. Okay? And here we increase the sample size. We have a sample size of 10, of 100, of 10,000 here. And you try to, of 1,000, sorry. We see how the base factor behave here. This is not the base factor, this is the posterior probability of model 1, but there is a direct connection between the two. And we use an IBC algorithm with 10 to the power 4 proposal from the prior. This is a Gaussian prior with variances equal to 4. And we take an epsilon which is equal to 1% of the distance quantile. Okay? So you simulate 10,000 simulation, we order the simulation according to the distance, and then you get the value of epsilon which corresponds to a quantile of the distance. I will go back to this point. This is also an important point. So this is this is more or less a k-nearest neighbor procedure. Okay, because and I fix the number of the neighbor here based on the percent of my simulation here. Okay. And what you observe when you use a summary statistic, which is a sample mean, median, and variances, even if you increase the sample size to 1,000, it does not concentrate it to 1 for the left part and to 0 for the right part here. Okay? And now if you change of summary statistics and if you use the median absolute deviation, it behaves like normally. And when you have 1,000 simulations, the posterior probability when model 1 is true of model 1 concentrated to 1, and when model 2 is true, the posterior probability of model 1 concentrated to 0. And there is 100 replicates here for each thing. Okay, so the way you will design and you will set the space of summary statistics is extremely important, the way you choose, the summary statistics. And what we have done with Natesh and Judith and Christian, this is a paper which we appear in Series B, and we try to derive sufficient condition on summary statistics for the corresponding base factor to be consistent. Let's say to asymptotically select the true model. So here we are far from ABC. I just try to see. In ABC we need to summarize. How to summarize to have a consistent model choice procedure? And that's a question which is more general than for ABC, but it has big consequences for ABC because in ABC we have to summarize. Instead, we have the curse of dimensionality with respect to the distance, and we are not able to discriminate correctly between different models here. And so let me show our results. So we consider that we have a sample, not necessarily an IID sample here. And so we have a summary statistic in dimension D, which has a true distribution, which is called Gn. And there are two competing models, model 1 and model 2. And under model 1, you have Tn is distributed according to distribution G1, which depends on the parameter θ1 of dimension P1. And for model 2, you have G2, parameter θ2, and dimension P2. Okay, here. And I try to see what are the different conditions on Gn, G1, G2, such that the base factor is consistent, select the true model, is one of the two is the true model. Okay? Let's just consider this case at the end. Here. And we have a set of 4 assumptions, not so strong because we have been able, I will say one word on this also at the end. We have been able to confirm, to check this condition on real summary statistics used by population genetics guys here. And the first thing is under the true distribution, you have a convergence in distribution of the summary statistics Tn. Okay. This is not a so strong assumption because you have a convergence at rate Vn here to a distribution which is called Q. And you have this sort of, let's say, asymptotic expectation, true asymptotic expectation of Tn, okay, which is called mu0. which is the guy which appears here, which is extremely important. And this is quite natural because often, and this is the case with respect to the number of markers in population genetics, summary statistics are chosen as empirical version of quantities of interest. And in population genetics, a lot of summary statistics are empirical average over the locus and over the marker, and you have a large number of markers, and these markers are almost supposed to be independent. There is a pre-processing to choose the right marker, and this is a lot of summary statistics are empirical average over the number of markers which are supposed to be independent. And then you have just the central limit. You have just the central limit theorem which apply to get this condition here first. The second one is under model 1 or 2, you should control the moderate deviation of Tn from his asymptotic mean. Okay, so look, here you got this guy here, the model asymptotic mean, which is called mu I of theta I, which now depend on the parameter value theta I, contrary to the true asymptotic mean, which is depend on not on the model here. And so under each model, Tn should concentrate around the model asymptotic mean value with the same rate Vn as the rate you get here. Okay, that's the condition. Yeah. On the posterior, let's say on the concentration of this. This is not a posterior concentration. This is a concentration associated to the model here. Let me now introduce a definition, and we said that model I is compatible with Tn if there exists a value of theta I such that mu I of theta I, so the asymptotic mean of Tn under model I, is equal to mu 0. Okay, the global asymptotic mean of mu 0, not under a specific model. Okay, and you say that model Mi is compatible with this Tn if you get this. So that means, I repeat, that the asymptotic mean of Tn is found within the range of the mean of Tn in model Mi. Okay, and for such model here, this third assumption only needs to hold on a compatible model, and it's okay. Often found in the Bayesian statistics literature here. So this is the behavior of the prior distribution of the mean of Tn near the true asymptotic value mu 0 here. So this is a standard. I will not have the time to really discuss this type of assumption. We use CVs here, and we use this prior concentration of the on this set here, and which is related to we introduce a quantity which is called Di, which is called the effective dimension of the parameter space, which concentrated. Look, you have the rate of concentration Vn, and so this Di can be viewed as the effective dimension of the parameter set, and this is a quite standard assumption we found in the Bayesian asymptotic literature when we would like to prove that the posterior distribution concentrated to a Dirac mass at the true value, let's say. You have exactly the same type of assumption here. Okay, and this assumption only needs to hold for the compatible model. And the compatible model, as you will see, will be the true. I will say, okay, one of the two models is the true. This is the compatible, and I should have this for this. And the exponent Di can be viewed as the effective dimension of the parameter under the posterior distribution. If Mi is compatible with Tn, the posterior distribution concentrates at this rate here on mu 0. On the posterior expectation. Okay, so you concentrated on mu zero at this rate. So you see, this is exactly the condition, standard Bayesian asymptotic literature condition here. And under the posterior distribution, mu I of theta I converges to mu zero at a rate 1 over Vn if you have this assumption. Okay? Here. So this is the concentration of the posterior distribution, and the posterior distribution concentrated at the rate 1 over Vn. Here. And last assumption is related to the tail of a compatible model compared to the true one here. And this assumption is automatically verified if the compatible model is the true one. Okay? So when we will only consider this case, I will give you a sub-result, so this assumption is in fact automatically verified. Look, because we have this result here, under these 4 assumptions, if the true model belongs to model 1, so there is a value of the parameter such that Gn is equal to G1 of this value of theta star, let's say 1 star. And if model 2 is not compatible with Tn, what does that mean? If you are not able to have a parameter value for model 2 such that the asymptotic mean of model 2 can recover the true asymptotic mean. Okay? If this is not possible, then the base factor is consistent. And the base factor based on the summary statistics Tn. Okay? So all is in the expectation. And why this is the case? This is clearly the case because asymptotically you concentrated to Dirac mass at mu 0. Okay? So if model 2 is not able to cover the value of mu 0, if there not exist a value of theta such that this is equal to 0, then you have a consistent model choice procedure. But if this is not the case, if M1 and M2 are twice compatible with the model, that it does not work. Okay? The base factor based on the summary statistics has the same asymptotic behavior as this, irrespective of the true model, and so we'll choose all the time the model with a smaller effective dimension, and then is not consistent here. Okay. I end 2 minutes. 2 minutes. I promise. So, one question: can we do better now using some sort of machine learning? So, why machine learning? And first, in practice, people do not have a fixed tolerance level. I introduced the ABC algorithm with a fixed tolerance level, but in practice, this is not. It does not work like this. The biologist guy say to me, okay, I have the cluster for 10 hours. I can simulate 10 million of data sets. Okay, they simulated in parallel a lot of simulated data set. They compare to the observed one. They order the distance and take a quantile of the distance. So the value of the threshold is never fixed in advance. And the tolerance level is a random variable, and the number of simulation is fixed. Okay? So in fact, real ABC algorithm for model choice is like this. You have a fixed number of simulation. It's your computational power. Okay? You simulate a lot. And so from the prior, from the parameter, new data set, calculate the distance, order the distance, and return the model index that corresponds to the n smallest distance. And n is a proportion of m, okay? With a proportion which is equal to 0, which is equal to alpha, sorry. And so the value of the threshold is a random variable here, which is taking as a quantile of the distance. Okay, it's a fixed quantile of the distance. This is a real practice of ABC. So, what is it? So, this is a sort of can-nearest neighbor approximation of the posterior probabilities. Okay, you simulate a lot. You have a learning data set, which is your simulated data set, and you try to find the best way to affect your observed data set to a class. A class is a model. Okay, so this is a supervised learning problem. Okay, and the standard ABC without any post-processing is just a k-nearest neighbor where the value of k depends on the number of data sets you have simulated. So what we are doing right now, and it's from 1 year, let's say, we investigate some ABC model choice techniques that use other machine learning procedure, and one good candidate we found is a random forest. Why is it the case? Because typically the biologists give us a large set of summary statistics, and in this large set, only a small number are important for the model choice things. Okay, so this is a sparse problem. This is a sparse machine learning question. Okay, you simulate a big learning data set, you control the number of learning data set, and you try to learn the best rule to affect your observed data set to a class, which is a model. And random forest is very robust, and is a very nice procedure to pick without any without any selecting any first selection of subset of summary data set. You let the random forest decide which variables are important or not. Okay, and so it works very well, and also you can use this to tune the ABC. Okay, because you can evaluate the error corresponding to the other guy you have simulated. You can put away like so you take some simulated model, you know the model index, you try to learn the model index and to minimize the error rate. And we are also define an error rate which is associated to our observed data set. And we are completely changing of things. We think that it's too difficult to approximate the posterior probability. We think it's possible with ABC standard rejection model choice to pick you get the order between the probability, so you are able to get the best model, but not to approximate finally the posterior probability. And this is exactly the same for all these machine learning things. They are not good to approximate the class posterior, the probability of each class given X, but they are good to rank the different and to select a model. And I am not with our biologists in a model averaging things. I just want to pick the right model. They are completely not compatible. Huh? They are very, very different. So now we are investigated a lot the use of machine learning strategy to tune the ABC approximation, and I think I should stop. I stop.
Okay, I think we've only got time for one question before we break for a coffee.
Yeah, for population genetics, I can understand that they try to model the coalescence approach to statistics, where you have a lot of parameter mutations. So and for my first question is for computing or approximating posterior probability. What can be the difference or the weakness of using forward and backward algorithms than ABC?
No, in my setting, there is no forward-backward algorithm to compute likelihood. Huh? There is nothing like that. Huh? I can't. I cannot compute. I cannot design an algorithm to compute the likelihood.
The posterior is where you want to estimate the parameters of interest using the posterior.
I'm not sure to understand well your point.
So you have some, like you want to estimate the mutation parameters. Or
yes.
Whatever it is. You have like a kind of probability of having the data, and then given those parameters. And when you reverse the posterior distribution,
Yeah.
the parameter for if
Yeah.
you want to estimate with a large scale data. So those are you're gonna have a lot of integration, as you say, that's gonna be really difficult to
Yeah.
deal with that. So what about the idea of using forward and backward algorithm on this kind of case? And
I'm
also for the to try to fit the parameters in the models. What can be the benefit of using because you don't know those parameters, you try to learn those parameters, even you don't know. But what can be the benefit of using like a hierarchical hidden Markov models, where you consider those parameters like one and then observe them? Then
I'm not sure to understand well, because an hidden Markov model is another model with respect to what I have. You would like to link the parameter and the data set with another type of approximation based on HMM, something like that, what you mean, and try to use this. I don't think it can be done for such model we are looking for. Such complex relationship. There is a very strong dependencies between observed DNA sample at the present time, and strong link between population, and there is no clever way to reduce, like the forward backward do the same thing, to reduce the integration space to design, let's say, approximation. Not sure it's possible.
Okay, let's continue this conversation over coffee, and thank Jean-Michel again for his talk.